Hi everyone, welcome to Chemistry Hotspot. Today we will be studying theories in coordination compounds. So basically these theories are of four types and we are classified among on the basis of evidence and then bonding. So based on evidence we have this Werner's theory. So this Werner's theory we have classified on the basis of evidence, and on the basis of bonding we have valence bond theory, then crystal field theory, then molecular orbital theory, or also we can call it as ligand field theory. So we have these classifications under theories of coordination compounds. So let us learn one by one in detail. So the first theory we have is Werner theory. Werner theory is proposed by Alfred Werner. He is also called as father of coordination chemistry. In 1893 he proposed these theories. So this theory mainly based on the concept that each metal in coordination compounds possesses two types of valencies. What are the two types of valency? Yes, the one is primary valency and the other one is the secondary valency. So it is the oxidation state of the central metal atom or charge on complex ion. Primary valency nothing but the oxidation state on the central metal atom or the overall complex ion charge we get. No, see, if this is the complex means the complex charge we are getting here. No, this is called as primary valency. Or what is the oxidation state present on this central metal atom? This is called as primary valency. So what does mean by secondary valency? Secondary valency is the coordination number. You know the definition for coordination number. The number of ligands which are joined to a central metal atom are called as coordination number. So here total 6 ligands are joined to the central metal atom. So this is the coordination number is 6. This 6 we call it as secondary valency. So the main definition for primary and secondary valency is, in primary valency you should consider the oxidation state of the central metal atom. In secondary valency coordination number is considered. So the next difference is this primary valency is satisfied by negative ligand only. The valency is satisfied by negative ligand only. Here it is satisfied either by neutral or negative ligand, and this valency is also ionizable, and here it is non-ionizable. Wonder how it is ionizable or non-ionizable here? Yes, it is because here the oxidation state of metal we are considering, and in this metal this is bonded to this outer sphere ions. So this bond is made up of ionic interactions. So this is ionic bond formation. Through ionic bond formation the oxidation state is created for this metal, and that is neutralized by air. So here ionic interactions we are seeing, so that this is satisfied by negative ligand only. Why? Because the oxidation state will be in positive, no? So if you want to neutralize it means you should always add the negative ligand so that it will get neutralized. That is why this primary valency is satisfied by negative ligand only. But in case of secondary valency it can be satisfied either by neutral ligand or negative ligand. As you know, that is this secondary valency nothing but the coordination number. For coordination number, whatever the ligand charge or it is neutral, that doesn't matter. All it matters is how much ligands surrounded by a central metal atom. No, so that is the case. And from that the next thing also comes that this is non-directional, and here it is directional, and I have already explained that this is formed by ionic bond. So this ionic bond has no direction, but this is coordinate bond. Coordinate bond always we symbolize this arrow. The arrow symbol itself says that it is directional, that is the electron from the ligand is passed to a metal, so it is in a direction. So this is directional. And the next is, this is represented by dotted lines like this, and this is represented by thick lines like this. And the example for this is cobalt 6 ammonia molecule, and this is balanced by this Cl3. This is the example, and this can be written in this form. This is like Werner's condensed form or condensed notation also you can say. In condensed form we can write it like this. In complex formation we are writing the same molecular formula complex in this way. And the next thing we are studying is the representation of that complex ion by Werner's theory. The representation I have given here, the general representation, that metal having N oxidation state, N plus oxidation state, which is satisfied by the negative ligand, that is marked with thick plus dotted lines. It satisfies both primary and secondary valency. Primary valency because the thick line satisfies secondary valency and this thin line satisfies primary valency. So this negative ligand satisfies both the valency. Whereas in neutral ligand it is satisfies only thick line, it is denoted with thick line, so it satisfies only secondary valency. In case of primary valency, the anion outside the coordination sphere, we consider it for the primary valency, or this is also called as counter ion. This can be well explained in our upcoming example. So for now, this general representation you just got it now. So the next we have, before going to the example, we have these 3 important points to be noted. What was that? Always charge on coordination sphere should be positive. Yes, we should know that we have the metal atom will be in an oxidation state, and the oxidation state of a metal atom always positive, right? So that is what the first point says. And the second point is, we should assume that coordination number should be 6 always. In general, the 6 coordination number will be stable. So if in the question they didn't mention the coordination number of the complex and given the form in a condensed one, then you should make that complex with 6 coordination number. And the third point is, neutral ligand written first followed by negative ligand within a square bracket. If I have this example, I have both neutral ligand and negative ligand. Ammonia is a neutral ligand, we all know, and chloride is a negative ligand. So first we are writing the neutral ligand, which is followed by negative ligand. This is what we have to follow when you are writing in a square bracket. Then the next thing we are going to study is the example. To get to know, understand this concept very well with an example, let me explain the thing. See, we have this example in a condensed form. Now I am writing this in the complex form. So I have said that you should consider the 6 coordination number. So I have taken the 4 ligand given, neutral as written first. Then in from negative ligand we have 4 Cl atom, and we need what? We need 2 Cl to satisfy 6 coordination number. I have written that here, and then I have written Cl2 Cl2 outside the bracket to satisfy the oxidation state of platinum. If I calculate the oxidation state for platinum, neutral, so 0 charge here, and from Cl you get 1 charge for 1 Cl atom, for 2 Cl atom you get 2 negative charge. So this -2 will become +2 oxidation state for this platinum, and this +2 oxidation state is neutralized by these 2 chloride ligands. So here the primary valency is +2 and the coordination number is 6, and this negative ligand satisfies both primary valency and secondary valency. I said it in before, no, this is denoted by both thick line and thin line because it satisfies both primary and secondary valency. How it satisfies? You can ask yourself, no? See, it satisfies because this chloride present within the bracket, and then this is contributing to the coordination number. So it satisfies secondary valency obviously. And you can ask, okay ma'am, it is satisfying secondary valency, how it is satisfying primary valency? Yes, because the oxidation state we are saying a primary valency, this oxidation state is arised not only because of this 2 Cl2, although this 2 Cl also contributing to the oxidation state of platinum, no? So this 2 Cl minus is contributed here, so that only we got this +2, and this +2 is neutralized by this 2 Cl minus. For this oxidation state, what and all are we getting here is, what and all involved here is this 2, all these 2 were involved, so that these 2 Cl are common to both primary and secondary valency. I think now you got this cleared. So here I have the example for the representation. So you can write it either in this way or in this way, that doesn't matter. All matters is you should satisfy the valency properly, and the denote you have to denote with thick line for secondary valency, thin line for primary valency, and for negative ligand you are denoting it with this. This is for the ligand within the bracket you should do. And as I said, this secondary valence is directional, you can denote it with arrow also. This representation we call it as Werner's representation. In general we write the complex structure like this, you know, right? The octahedral complex is written and this counter ion is written outside the bracket. It is general representation. They will ask in exam that write Werner's representation for this compound. They may give in condensed form or in a complex ion form, or they can give this complex structure and they will say to write in a Werner representation. in BSc exams you can see this type of questions, and you can also see the difference between the primary valency and secondary valency. They can ask for 2 marks. And the next important thing, as I said, Werner's theory is based on the evidences. So the evidences and application of this theory, if you are considering, the first and foremost evidence is the molar conductance. You have to understand this concept by considering the few examples or few concept of what and all proposed by Werner. When Werner started, he is named for father for coordination chemistry, because he started studying these complexes, this color of the property, sorry, not the color, the properties of the complexes, what and all properties they are having. Like that, when he started these studies, he used to take this complex having different coordinations, and he treated it with Ag plus, and he get these following PPTs. Based on this, he considered that okay, I am treating the compound with Ag plus, I am getting 3 AgCl at first, and when one ligand I have made it less, I am getting 2, and as reducing each ligand I am getting lower the mole. So what he got to know that as from first compound to the last compound, the molar conductance decreases. Why? Because the ions released also decreasing. The Cl ion we are having here, see, this Cl ion outside the bracket only reacts. The complex ion won't give you reaction. Only the ion present outside the bracket reacts with the Ag1, and you will getting the PPT AgCl. So as the ligand outside the complex decreases, the molar conductance also decreases. As you know, molar conductance is given by the ions present in the solution. So when the ions is only not there, means how can it give the conductance, right? So we have got this evidence from first to last, conductivity is decreased because the ions present is decreased. Next property is cryoscopic measurement. This is also called as colligative property. Here, depression in freezing point increases with increase in number of particles. If the particle number is increased, it means the freezing point depression is also increased. Well, how you should consider the particle? Always a complex ion is one particle. Don't make it like if it is a complex ion or 6 ammonia is there, 1 metal is there, so 7 particle, that is wrong. Complex ion should be considered as 1 particle, and other outside we have 3 ligands, so total 4 particles. Here complex ion 1 particle, Cl 1 particle, total 2 particle. Particle is more in case of first one, so this is having more freezing point than this one. So this evidence is for cryoscopic measurement. Another evidence is the precipitation method. The precipitation method we have, as I explained before, the molar conductivity. Now same example for this also. When Werner Alfred started to studying these complexes, he noted the PPT formation. In first case, 3Cl minus reacts with this Ag plus, forming 3 AgCl as a PPT. So 3 moles of AgCl is got. As we decreasing the ammonia number, the PPT is also got reduced. The number of moles is also reduced. If it is getting reduced, means the formation of PPT is also got reduced. So the PPT formation order from the compound above to down getting reduced. So this method proves that if the number of ions are getting reducing, means it is also reduces the formation of PPT. This is precipitation method. So we have the application of molar conductance, cryoscopic measurement, and the PPT formation. These 3 evidences proves or favors the Werner's theory. And yes, it is favoring the Werner's theory. So if it is favored and if it has no limitations, means there wouldn't have any VBT or CFT or ligand field theory, right? Yes, you are guessing it correct. This theory also has the limitations. So only we are studying further more theories. Well, what are the limitations for this theory? It doesn't explain the color or electronic spectra of the complex. Electronic spectra of complexes or color of the complexes, it doesn't give any explanation. and nature of ligand was also not explained. Whether the ligand is strong field or weak field, that is not explained by this theory, and no explanation given for magnetism, that is electron pairing. If electron paired means we will say it is diamagnetic, if unpaired means we will say it is paramagnetic. This explanation is also not proved by this theory. So these were the three major limitations of this Werner's theory, leads to the further studies for valence bond theory. So valence bond theory we are studying because of these limitations. Further scientists came up and they also done their research and brought up this valence bond theory followed by this Werner's theory. Okay guys, this is all for this video. In my next video I will be discussing this valence bond theory. I hope you guys understood what and all we have studied in this video. Yes, let me recall all the things once in a brief way. We studied Werner's theory, valence bond theory, molecular orbital theory or ligand field theory, and CFT. These four classifications we have studied under the theories of coordination compounds, and Alfred Werner, who is the father of this coordination chemistry, proposed this theory in 1893, and it is consists of primary and secondary valency classification. Primary valency nothing but oxidation state, secondary valency nothing but coordination number. And we have studied the representation of that in a general form, and we have given example and studied the representation in detail. So we have studied the evidences for these theories, that is molar conductance, and also this also explains the precipitation method, as from compound first to last compound the precipitation decreases. So this explains the precipitation. Same time it also explains the molar conductance. Then we have this cryoscopic measurement. Then we studied the precipitation method and the limitations, these three limitations. And yeah, one thing I have forgot to mention here, these conductance we have these compounds. No, these compounds are in which state? Condensed. So I have said it before, condensed representation. These are in condensed representation. This condensed representation of the complex can be written in the ionic complex representation as follows, like this. What you have to do? You have to satisfy the 6 coordination number, and the remaining ions are written outside the bracket. Well, what and all we studied today is all about Werner's theory and its applications, and then the limitations. Well, I hope you guys liked this video and found this video helpful. If you are found this helpful, please don't forget to subscribe my channel and share this to maximum people. Thank you for watching.